answer is all these values in here. And that stinks for all sorts of algorithms. And there's no way getting around that, and that happens especially with our age variables. Okay, so what's the right thing to do? The right thing to do is be aware that it could matter what your algorithms are. It typically doesn't matter. I use cluster analysis as an example of where it does matter. If you choose the default, which is often in most software packages is something like FastClust, it's going to get a terrible answer most of the time. Not all the time. So why do they use this? Because it gives the same answer every time. My algorithm stinks. I assign you guys all to run this algorithm. What's it called? Anyway, I don't know what it's called. But there's variations on the theme in all software packages. And it's going to say, well, how many random starts do you want me to use? Basically, if it says, how many random starts should I try, you know it's doing this, something like this, which is good. You tell it 10. And guess what? Everybody in the class comes back with a different answer to the same darn data set. The data set's not any different. And everybody got a different answer. That's terrible. Which one should we publish? Well, guess what? We should find out which one minimizes the objective function, and then we have what might be the best answer. So, lots of people don't like this algorithm. But that algorithm gives a stupid answer most of the time. So they need to get over it and use a more computationally intensive. So the computation here is more than t times the computation over there. We like to choose we like t to be really large. If we can choose it in thousands or hundreds of thousands, we do that. And you can actually count where it converges, because there aren't that many places where this thing can converge. Either, depending on how many points you get in each cluster, you can't converge to that many different places. And that's another way we check to see if we got the supposedly right answer. Are we finding, as t changes, are we finding more and more different solutions? Then we need to run it more. If we're finding all the same solutions that we found before, then we're probably close to done. And this is what people don't like. What do you mean probably close to done? Well, that's and we can make mathematical definitions of that. We haven't found a new one. We've tried 1,000 new ones and haven't found a new solution yet. Therefore, I claim that we're done. But I still might not have found that one point. This is why things like principal components are still important, because that point is identified in different ways. And just feeding it into a cluster analysis is not necessarily a good idea. So again, any p-values? No p-values. It's all computer science and math. And so there's calculus in this part, still no p-values. By the way, why do we get p-values here, or in the calculus part? We get p-values because of more derivatives. More derivatives tell the rate of change of something, and more derivatives equals standard errors. Why are there no standard errors in certain problems? Well, in cluster analysis, there are no standard errors because there's no variability to assess. Can we put confidence intervals around these things? Nope. If we do logistic discriminant analysis, we can put confidence intervals around it. If we do logistic regression, we can do confidence. There's all this stuff we can do. But people like to do cluster analysis, and I understand that it's interesting to group the points together and see what happens. But my warning is that if you do cluster analysis, you have to be careful about the algorithm that you're using, and you have to realize that it might give you nonsense. If the clusters are real, I guess there is a lesson. If the clusters are real, then a fastclust algorithm might find the right answer, and an algorithm where you get to pick the number of random starts very likely will find the right answer. If the clusters aren't real, then you get a whole bunch of gibberish. This lesson has been learned by many of my biological colleagues. Because they say, well, we got to do a cluster analysis. I said, fine, here's your cluster analysis. This doesn't make any sense. That's what they come back with. I can predict the email. I said, okay, here it is. They come back every time. Lots of times. This doesn't make any sense. Didn't I tell you in the first place it's not going to make any sense? But they didn't believe me because they like the papers that they see have cluster analyses. Well, there's a bias. The cluster analyses that they see is because they ran the cluster analysis and it gave something intelligent. So it went in the paper. Same thing with principal components. The same thing with there's a publication bias that you need to be aware of. So don't do cluster analysis blindly. I guess that's the lesson. Or if you do it blindly, then be wary of answers that don't make any sense. All right, questions? We have a minute. We have a few minutes. Yeah, now you're an algorithm expert. There's entire courses in this. Go to the computer science department. There's some course. I have no idea what it is. Is there a course? Oh. All right, we're done. The next week I may have jury duty, I may not. But you get Dominique and you can learn about sample weights, which are super cool and something you should know about. If you do surveys without weighting, then that's bad. Because your responses are biased, probably. But not necessarily. All right. Now I have to erase this part because it's not mathematically correct. Oh, I just said that on the camera.